Good afternoon and welcome to my presentation. My name is Matic Ivancic and I'm a researcher in company Rasol, which is part of Magi Scientific. Today I'm going to talk about the method for the detection of mineral dust concentration, which is based on measuring optical absorption of dust aerosols. So why to measure mineral dust? Mineral dust is important natural source of aerosols, which can strongly influence their quality and has an impact to global warming cycle with light absorption and scattering. Sand and dust storms are also mentioned in new WHO report published this year. The measurements and predictions of dust events are required by WHO guidance to take measure in time with aim to minimize the effect of dust to health. The Sahara Desert is a large source of dust and PM10 in general, and frequently it can influence the local air quality in Mediterranean and further north in Europe. To our knowledge, there exists no direct method to measure dust concentration locally and in real time. So the new method I'm going to talk about today was developed within the international project DNEP, where acronym DNEP stands for Detection of Non-Anthropogenic Air Pollution. Our company was responsible for project coordination, and we developed a method together with partners from Josef Stefan Institute, the Cyprus Institute, Institute of Environmental Assessment and Water Studies from Barcelona, Eurovisia, and Helmholtz Centrum from Dresden. Initially, the measurement campaign was planned for a period between February 2019 and July 2020, but we extended the campaign and the instruments are still running on sites in Spain, Cyprus, and here in Ljubljana. To explain how the lab method works, we have to understand some properties of mineral dust first. Here we have a picture from electronic microscope. Several pieces of mineral dust can be observed here, and we could see also some black carbon was captured at the same time. So here is black carbon, and these bigger particles, bigger aerosols are mineral dust. The black carbon is strongly absorbing refractory elemental carbon, and it is an important marker for the anthropogenic air pollution. It is a consequence of incomplete combustion, and wildfires are the only natural source of black carbon. The light absorption on mineral dust is weaker than the light absorption on black carbon, which makes it difficult to develop a method to measure optical absorption only on mineral dust. Fortunately, we could take an advantage in the second property of mineral dust. Mineral dust is usually bigger than 1 micrometer. It is in so-called coarse mode, while the black carbon is usually smaller than 1 micrometer. It is in so-called fine mode. This fact could be also easily observed from this image. So the key for our method is to concentrate the coarse mode of aerosols to enrich the mineral dust content in the sample. For this purpose, we developed a special size selective inlet with high volume virtual impactor, which I will explain with following slides. Firstly, here is a sketch of ordinary inlet without any site selection. The black carbon and mineral dust are mixed, and as I already said, the light absorption mineral dust is shadowed by black carbon. On next slide, here is a sketch of a high volume virtual impactor where we are using two different flows. Major flow is around 100 liters and per minute, and minor flow is 2 liters per minute. Because black carbon is smaller, it has lower momentum. Therefore, it's easier to change its trajectory. On the other hand, coarse particles are bigger with higher momentum. They are steering in initial direction with such setup. So with this setup, we are throwing away the fine mode aerosols with the major flow. So basically, majority of strongly absorbing black carbon is removed. With the minor flow, we are then sampling aerosols in coarse mode, which could be further analyzed. On the left, we have the inlet developed within the project. On the right, we have some laboratory results. Concentration efficiency is shown with the blue line. Average aerodynamic volume size distribution for, let's say, normal inlet is presented with black line. But because the concentration efficiency is bigger for bigger aerosols, we could see that the peak of the volume size is shifted to bigger aerosols, in this case of inlet with virtual impactor. We defined the enhancement factor, which is the multiplication factor that reflects the enrichment of coarse fraction downstream of VI. So the enhancement factor is the characteristic of our setup, and it was estimated to be equal to 11. To measure optical absorption, we used a talometer. It has dual spot algorithm, which offer us to compensate nonlinearities coming from loading effect in real time. It has 7 wavelengths, so wavelength-dependent optical absorption could be measured. Dust and black carbon have different spectral dependence of optical absorption. The absorption Angstrom exponent of pure black carbon is around 1, while mineral dust absorbs light more efficiently at lower wavelengths. Therefore, the lowest wavelength 370 nanometer is the most appropriate for the separation between the light absorption mineral dust and black carbon. And of course, if we want to transform the optical absorption to mass concentration, we need a calibration constant called MAC. So mass absorption cross-section. MAC for black carbon is well known. The MAC for dust will be determined at the end of the presentation. Here is our methodology. There are two talometers, one with virtual impactor as inlet and another one with PM1 cyclone. With the talometer with PM1 cyclone, we measure anthropogenic contribution to local pollution, because black carbon is the only light absorbing aerosol within fine mode. With the talometer with VI inlet, we are analyzing the optical absorption on coarse aerosols, but because the efficiency of VI inlet is finite, all black carbon cannot be removed from the sample, as we also marked in a sketch 3 slides ago. Anyway, we can correct the mineral dust light absorption estimation for mined black carbon in coarse mode sample with the enhancement factor, which I already said is the characteristic of our setup. So here is the estimation of optical absorption on pure mineral dust. We have to subtract the measured absorption on the instrument with PM1 inlet from the absorption measured on instrument with VI inlet, and we have to weigh the difference with enhancement factor. Finally, mineral dust concentration is estimated from the optical absorption with calibration constant MAC. Okay, so simple proof that our size selection is working is the color of the filter tape. Here we have 5 filter tapes with installed different size selective inlets from Ljubljana and Barcelona. All images here are slightly saturated to increase the visibility. On the left side, images are from, let's say, normal operation, where the presence of mineral dust is not expected. All dots are black, also the ones from a talometer with VI. On the right side, we have pictures of filters sampled during dust event. On the tapes from instruments with PM1 and PM2.5 self-selective inlets, the dots are still gray because mineral dust is in coarse mode and is not sampled here. But the color of filter dots from instrument with VI are yellow, as it expected for mineral dust. We investigated filters collected during our campaign also into more details with helium ion microscope. First, we have prepared the helium microscopic images for the filter tape from instrument with PM1 inlet. On both picture, we could see a lot of microfibers, which is actually the structure of our filters. On the right zoomed image, the microstructure of black carbon can be also nicely observed. On the second slide, the helium microscopic images are shown for the filter tape from instrument with VI inlet. We can see again the microfibers as a structure of filter tape. The dust aerosols can be already observed in non-zoomed image on the left, and detailed structure of giant mineral dust aerosols on right side. If we zoom the right image further, we could find also a black carbon on the same image. We can see also a black carbon here and here. So this is just confirmation that the correction for absorption on black carbon is required if we want to use our method. Before we continue with the results, I must give you some information about uncertainties of the method. Taking different uncertainties into account, the overall uncertainty is estimated to 40%. And here we have the estimation of the MEC from 3 stations. On x-axis is measured optical absorption on mineral dust, and on y-axis is the estimated concentration of mineral dust. MEC value is 1 divided by the slope. Dust was estimated with 40% method in Barcelona and Ljubljana, while the dust events in Cyprus are too frequent for this method. Therefore, chemical analyses were used there for the dust estimation. The plot is in logarithmic scale because the dust is estimated along 2 orders of magnitude. You can see nice correlation, especially for higher concentrations, and some more uncertainty for lower concentrations, as expected. The common MEC estimated from whole data set was equal to 0.15 square meters per gram. We prepared the MEC estimation also for each station separately. You can see only minor differences between these stations, which confirm the overall usefulness of the method. For the station in Cyprus, we split the MEC calculation regarding the source region, the situation when the dust was coming from Northern Africa and the Middle East. So the dust from Middle East was slightly less light absorbing with a slightly lower MEC value. We can compare the MEC for dust with MEC for black carbon. So we can see that the ability to absorb light is more than 100 times higher with the black carbon. And these are the results of more than 2-year-long measurements. Here we compare the dust concentration with orange with PM10 measurement presented with blue. The station in Ljubljana and Barcelona are characterized as city background, while the Agia Marina in Cyprus is regional background station. On the left side we have time series, and the mass closure is on the right side. Ljubljana and Agia Marina, the dust concentrations are always lower than PM10 measurements. You could also see higher dust contribution during intensive dust events, like here and here. The mass closure for Barcelona is not so good. Most probably the reason is the complexity of the site. It is a mixture of urban pollution with possible local dust influence during the dry period. One benefit of the presented method is to study dust intrusion into more details with high temporal resolution. For example, we can check the situation from May 2020 in Cyprus. Air masses were advected to Cyprus from northern Africa with some detour over Greece and southern Italy. The concentrations of dust were not equal all the time, but aerosols were coming in waves. Maybe we can check another interesting event in Ljubljana from March 2020. We could see that our method underestimated the amount of dust in this situation. The same could be also observed on scatter plot here. In this situation, the dust was advected to Slovenia from Asia and not from Northern Africa, which is usually the case. The source region for this non-usual event was desert near Caspian Sea. The mineral and chemical structure is most probably different in this region. Most probably the MEC estimated from our other data was too high for this event, which led into underestimation of dust concentration with our method. We can conclude that the possible variability of MEC is the biggest drawback of the presented method. We showed it works fine for dust advection into Europe for known source regions. To summarize our talk, we developed a method to separate the natural and anthropogenic contribution to air quality. Method is automatic, offers us real-time analysis with high time resolution. We tested the method with more than 2 years long dataset. If you would like to learn more about the project, I would like to invite you to visit the project webpage, where the results are also published in real time. We started also a new campaign in Qatar this year. Just 1 week after installation of the instruments, very intensive dust storm happened. You can see it in a video on the left. The dust concentration exceeded 500 micrograms per cubic meter. Our instrument survived the storm without a problem. Qatar is also an interesting location because there is an interesting mixture of local white dust, reddish transported dust from Saudi Arabia, and strong anthropogenic local pollution. So I'm really looking forward to analyze the Qatar dataset. At the end, I would like to invite you to a presentation on Thursday morning. Balint will talk about the dust storms in Qatar. He's now a member of our team, but before he worked in Qatar for several years. And finally, I would like to thank our Ministry of Economic Development and Technology and the European Regional Development Fund for the financial support for the DINA project. And the most important, I would like to thank you for your attention with the postcard from Ljubljana. Thank you.